So large language models memorize some of their training data. And in this video, I want to show you how you can extract which data LLMs actually end up memorizing, and also discuss the extent to which this memorization ends up happening. As a quick recap, the training process of an LLM, we start with collecting a bunch of training data and use this to train it, such that after training, we can use the model to prompt it to generate all kinds of different outputs. And over the last couple of years, AI companies have seen dozens of copyright lawsuits being filed against them exactly over how they're actually using this training data. For example, Getty Images is suing Stable Diffusion for scraping its content. The Times is suing OpenAI for using copyrighted articles. There's a lawsuit against Perplexity AI, and as this article in The Atlantic highlights, whenever Meta was training its llama models, they were actually relying on LibGen, a source of books that are pirated. Now, whether related or not, after the lawsuit, when Llama 4 dropped, the reception of it was, so to speak, not amazing. The performance was not as good as people had actually hoped for. Now, while the full training data of all these models is not publicly known, it is also not really a secret that these LLMs are trained on trillions of tokens of digitized creative works. For example, one popular dataset is FineWeb, which contains 15 trillion tokens scraped from the internet, meaning that it contains all kinds of things like blog posts, news articles, comments. Also, books themselves are extremely valuable in the training process, so fiction, non-fiction, academic books are all leveraged when training these models. And more recently, OpenAI struck a deal with some libraries across the UK to potentially even start training on archives, digital copies of all kinds of archives books. Now, what this means is that whenever we are interacting with these models, we are creating derivative works of frequently copyrighted material. And the questions that lawyers are interested in is whether the way these models use the data can fall under this fair use policy, which allows users to use copyrighted works in ways that are considered fair. And the question then becomes, what does fair use look like for AI? And while that's a question that the lawyers are interested in, a question that I myself find interesting is also whether the way these models are building and leveraging their training data is really that different from the way that humans would do it whenever they're creating new works. For example, if you've ever had to memorize a poem when you were little by reciting it over and over and over and over again, you might find that even 10 years later, when you're prompted with a little piece from this poem, suddenly your brain starts to generate it completely without a single mistake. Or have you ever written an essay where you pulled some ideas from a few books that you like, you borrowed a clever phrase here and maybe mimicked, the style or the tone of another author that you like? And the point is that generative models turn out to not be so different from these two examples that I just gave you. They also are found to memorize their training data, and they're also found to recombine at times verbatim examples from their training data sets. As a few examples, in the lawsuit that New York Times is doing against OpenAI, one of their examples is that the model actually ends up completing the remainder of a paywalled article when prompted with a small piece from the article. So in this case, it's an article that won the Pulitzer Prize about taxi drivers. And when the model was prompted with a piece from this article, even though it's paywalled, ChatGPT still ended up completing it verbatim. You can also find that these models can be prompted to recite chunks from known books. So what I'm doing here is I'm using Meta's Llama 3 8 billion parameter model, and I took a bunch of different Harry Potter quotes that I found on Goodreads. Now I prompt the model by inputting a part of this quote, and then I see what is the model actually giving me as output. And as you can see, the completion that the model ends up giving me is actually an exact copy of the original quote that was in this book. some more examples here where the model, at least initially, starts off by completing it exactly as it is in the original quote, while eventually diverging into something slightly different from, quite a bit different from the original quote. Or one more example where it also, save for one word, ends up completing the quote verbatim. So basically, by taking a prompt that contains part of a quote from a book, I can regenerate exactly the remainder of this quote, in this case from Harry Potter. And even when asking the model for help in more day-to-day tasks, so not necessarily prompting it with these pieces of training data, of potential training data, but asking it for help with, for example, writing a letter or a tutorial, what was found in this recent work on measuring non-adversarial reproduction of training data is that even in these kind of day-to-day naive tasks, up to 15% of the output that these models gave were shown to overlap with snippets that could be found on the internet. So for example, when prompting the model to write a news article about gravitational waves, part of the output that the model ended up giving was exactly present on the internet. Now, besides copyright concerns that the lawyers have, and besides generally this question of how do models recombine their training data that I have, another issue with this kind of verbatim memorization is that this also leads to user privacy risks. So something that I recently did, I uploaded a bunch of codes to GitHub where I accidentally left in my GitHub access token. And so imagine that data was scraped by some model builder, such that, the next time someone was using GitHub Copilot, when he started writing or she started writing their GitHub access token, the model ended up completing it with my thing. So clearly, there are these kinds of user privacy risks that are attached to memorization, where the model might complete sensitive data with certain prompts with sensitive data. All right, so now that we've seen a bunch of examples of how these models are reusing their training data and the potential risks around that, let's dive into the technical details of how do we actually extract the training data from these models. Now, the first setting that I will consider is a setting that is, in a way, the most complicated one where I assume that I know nothing whatsoever about the training data, and still I would like to somehow find a process to generate data that I could check whether or not this is part of the trained data or not. So the way we can formally define this kind of memorization is using this notion of extractable memorization, where we say that an example is extractably memorized if an adversary without access to the training data can somehow construct a particular prompt that would elicit the model to produce this specific training example X from our training data set. And then the big question in this extraction methodology is, which prompt do we actually choose? How do we find this P such that we can get the model to elicit X's that were in our training data? Now, the authors of the original work extracting training data from large language models proposed several ideas. So their first idea was around, let's just start with a one token prompt, such as some kind of start of sequence, beginning of sequence token, and simply start with that token and sample a bunch of different completions from the model with a high temperature initially, such that we cause the model outputs to be more diverse, and eventually decaying the temperature to not steer away from memorization. So once we enter this kind of memorization path, to have a low temperature to stay on that generation path. And while this one token prompt can work, you might want to enforce somehow even more diversity to have your model generations really cover a wide space of generated data to increase the chance that something in that generated data is going to be part of your training data set. And for this, the authors propose to scrape the internet and just take different kinds of prefixes, different kind of little chunks from this internet data, and in the same way, starting with a high temperature, sample with these little prefixes instead of simply this beginning of sentence prompts. Now, suppose that we follow this methodology. So suppose that we sample a bunch of different completions, either from this beginning of sequence token or from whatever little chunks we found on the internet. And we end up with a bunch of different generations. How do we actually assess whether these generations could have been part of our training data set? Are they members from our training data set or not? Now, in order to do this, what we could use is some kind of signal, some kind of quantity, for which we know that this quantity is, for example, high if the data point was part of our training data and low if it wasn't, or the other way around. So some quantity that would allow us to distinguish trained data or not. And one such signal could be the perplexity, since having a low perplexity over this sequence essentially would mean that the model is not particularly surprised by this sequence, and hence it could have seen it before, for example, in its training data set. So if we compute the perplexity for each of our generated sequences, potentially we would find that some of them have a very low perplexity because they correspond to, in this case, my examples are existing Python code or an excerpt from Robert Sapolsky's Behave book. And the results that the authors find on the model that is GPT-2 is that they are able to find different kinds of memorized content, such as personally identifiable information such as names, phone numbers, addresses, social media accounts, URLs that are linking to working web pages, all kinds of different codes, news articles, licenses, and even tweets. Now, what the authors did is they generated 200,000 different samples, all of them being 256 tokens long. And out of all of these different generations, they found 604 memorized training examples. So out of all the data that GPT-2 was trained on, which is a 40 gigabyte training data set, within this way of prompting the model to just generate different kinds of samples and assessing membership using a membership inference signal, in principle, the authors established this lower bound of 0.000000015% of the training data being memorized. While it is low, it is some kind of starting point, some kind of lower bound that we found without any kind of knowledge about our training data set, and simply by prompting the model and using a membership inference signal. So this gives us some notion that yes, content is getting memorized. Now let's see if we can improve upon this lower bound if we actually assume that we do have access to the training data. So to define again this notion where we do have access to the train data, we would say that an example P concatenated with X from the training set, so both P and X are from the training set, is discoverably memorized if whenever we put P into the model, we are getting as output X. So prompting with a piece from the training data, we would call X discoverably memorized if prompting with that P would lead to X. And here the question of which prompt to choose is a little bit simpler because we have access to the training data for which we want to test, is it memorized or not? So what we can do is we can randomly sample all kinds of different chunks from this training data of a particular length, and then just have the model complete all these different chunks, and then we would see, we would check whether the completions are also part of the training data, then we call it memorized, or if they're not, then we call it that particular piece unmemorized. And what are the results in this case? Similarly to the previous results, we find all kinds of things like quotes, licensings, codes, and also excerpts from books, as I showed you before with Harry Potter. And so by conditioning on chunks of the training data, we can improve quite a bit on this lower bound that we initially had. And in this case, the authors from Quantifying Memorization Across Neural Language Models find that at least 1% of the training data, in this case of this GPT-Neo model, is discoverably memorized. And an interesting question here is also around this length of the prompt. So as I said, we select the prompt by chunking up the training data and by selecting different kinds of lengths that we will then input into the model. And this length is actually a kind of critical feature of how much discoverable memorization we will actually find. So as the authors show in this graph, if we're using sequence lengths of 1,000, we get much higher rates of extraction than if we were to use much shorter pieces from our training data, which is in principle not very surprising, right? Like if you're using a lot more data and prompting the model with that, you're kind of biasing the model much more into this correct direction of like, hey, this is what I want you to generate, as opposed to with shorter chunks where, potentially the generation can go in any kind of different direction. Now, another work, Rethinking LLM Memorization through the lens of adversarial compression, also relates the length of the prompt that leads to a particular memorized sequence can also be linked to this notion of compressibility. And I only briefly mentioned this, but the authors in this work define this compression ratio as the length of the generated sequence divided by the length of the prompt that was used to generate the sequence. And they kind of test what kind of data is, what kind of types of data are more compressed, so are extractable with much shorter prompts versus less compressed. And what they find is famous quotes, for example, are compressed, have a very high compression ratio according to their definition. So, anyways, all of this is to say that with this kind of methodology, we find that at least so far, about 1% of the training data can be extracted. Whether this number is large or not, that is a subjective measurement or a subjective assessment. However, in any case, it's quite interesting that we're able to find that 1% is really so imprinted in the model's mind. And so the next question that I'm interested in asking is, what is this data that the model likes to memorize? So what particular data points get really verbatim stored in the model weights? The first observation that is made is that rare but frequent examples get memorized. So this is a result that was shown in some previous work, what neural networks memorize and why, where the authors noted that memorization is necessary for achieving close to optimal generalization when rare and atypical instances make up a significant fraction of the data distribution. So suppose, this is like the semantic space in which our data points live. We have some clusters of data points, and we have a few of these data points that are kind of like outliers. So the only way for the model to achieve good performance on these far away points is essentially to memorize them, because it cannot really generalize the properties that it learned on the other clusters to this data point. So if the model wants to perform on this kind of rare and atypical instance, the only way is to memorize it exactly. And since the model is incentivized during training to push down its loss, it is not unreasonable that the model starts to think, hey, well, look, I'm encountering these rare examples relatively frequently. They seem important. I cannot really leverage what I've learned from my other data points to predict on these guys. Hence, I just end up memorizing them exactly. And as examples of what the authors in this paper find that the model memorizes, for example, for a class of images, bobsleds, what the model ends up not memorizing are kind of like very expected images of bobsleds, so the ones that you see on the top row, while the ones that are memorized are bobsleds in slightly strange, unexpected environments. So really these kinds of like atypical instances that have slightly different features than your original your more classic bobsled images. Now, what the authors from quantifying memorization across neural language models found is that it's not just these rare instances, but also what is important is that the strings that get memorized are the ones that are frequently duplicated. So the string that is only seen several times in the training data rarely is memorized, as this graph shows. So the number of repetitions that a particular string has matters as to whether or not we will be able to extract it verbatim or we won't be able to extract it verbatim. And in principle, I also think this is perhaps this is even something that we would want. Since if something is popular, it is repeated a lot across the internet. And just like when I had to memorize poems by repeating them very, 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 very often because, for some reason this poem was deemed important, I just decided to memorize it. So if the model again sees a particular data point scattered in different places very many times, it is not strange that it ends up completing it verbatim. It ends up memorizing it exactly. So another property of the data points that get memorized is that frequently repeated samples get memorized more. However, what I want to highlight, which is interesting, is that while the trend is clear, more repetitions, more memorization, there are certain examples that have been seen only a handful of times, and the model still decided to memorize those. So here we might be coming back to these atypical instances that the model for some reason still finds important, but has no other way of learning about besides exact memorization. And as to how, or to link it to how our brains work, there are certain events in my life that, even a single exposure to a particular phrase, a smell, a chord, a picture, somehow made it completely unforgettable. And examples of when the model ended up doing this are unfortunately less exciting. They're mostly text examples that have a very simple sequential structure. So here we see a bunch of different examples that the model still memorized, even when it was only exposed to it a handful of times. And typically, again, these are examples with a very simple sequential structure, boilerplate code, or frequently repeated text that, while starting off unique, in the end ends up being like some standard piece of text. So overall, easily completed sequences. Now I wanted to think a little bit more about what these properties that drive memorization are. And to start, I wanted to test what I had done for Harry Potter, whether I could also repeat it with another book, The Lord of the Rings, which I think is an equally popular book, with equally kind of potentially sometimes strange terminologies being used, like a particular language that is not exactly our standard English language, with lots of different names and cities and so on that are strange. So what I did, again, same thing, I took all these different quotes and passed them through Meta's Llama 3 8B model. And I again found that the model at times manages to complete exactly the sentences. So here I prompted it with, "It's a dangerous business, Frodo, going out your door. You step onto the road, and if you don't keep your feet, there's no knowing where you might be swept off to." Model completed this correctly. But then I also had quite a few quotes that the model was not able to complete exactly. So here I prompted with, "We are truth speakers, we men of Gondor, we boast seldom and then perform or die in the attempt not," and then the model went off in a wrong direction. Or similarly here, "Beneath the stars of ever-even Aldemar, it's shown in Eldemar beside the walls." Again, model completed it in not the right way. So here I started to think, okay, what is the difference between this completion with Frodo that it did exactly, so this quote that it memorized, versus these other two quotes that it ended up not completing correctly? And if we think about it, the original quote that it did complete somehow has a low entropy and potentially a high mutual information with the training dataset. So what I mean by that is that it doesn't contain too much of this strange terminology, these words that are not really in the English language. And hence the model might think, okay, this sample is rare, or I've seen it sufficiently many times, let me memorize it. While these other two samples, they contain a lot of strange words like Eldemar, Gondor, and the style is a little bit different. So the entropy of these samples and potentially is very high, and potentially the mutual information with other samples in the training data that the model is seeing could actually be quite low. So that the model decides to not memorize these guys, even though, again, it might be rare, it might be beneficial to decreasing the loss, but apparently not sufficiently so to sufficiently useful to decide to learn them. So what I want to conclude from this is that, in a way, data must still improve the world model that the LLM is building internally. So somehow, whatever it decides to learn from, even the things it decides to memorize, should somehow improve performance on other data points, at least a little bit as well. And if the language is too high entropy or like too foreign, these are things that might not end up getting learned by the model or memorized. And finally, I want to link this to an article that I also quite liked reading, which is called Driven by Compression Progress. A simple principle explains essential aspects of subjective beauty, novelty, surprise, interestingness, where the author says that, Jürgen Schmidt-Huber says that data becomes temporarily interesting by itself to our brains once he learns to predict or compress the data in a better way, thus making it subjectively simpler and more beautiful. So the things that I kind of pay attention to, I pay attention to them because they are helping me reorganize the world model that I have such that I can compress whatever I have in a better way. Curiosity then is the desire to create or discover more non-random, non-arbitrary, regular data that is novel and surprising, but in the sense that it allows for this compression progress because its regularity, the properties of that data point that I'm paying attention to, wasn't yet known to me, but again, was useful. And this drive maximizes interestingness, the first derivative of subjective beauty or compressibility, that is the steepness of the learning curve. It motivates exploring infants, pure mathematicians, composers, artists, dancers, comedians, and since 1990, artificial systems. So I thought this was a very nice way to think about which data is in a way interesting to the model, whether or not it ends up memorizing it, at the very least, which data it ends up using in order to change its world model that it already has. Okay, now you might think, all right, we have seen that these models memorize 1% of their training data. Surely one way to avoid this memorization is simply to align, aka fine-tune the model to not regurgitate, so to not verbatim spit out particular chunks of training data. How this aligning would look like: whenever we are doing our instruction fine-tuning, we would basically just fine-tune it with data points like, whenever I prompt it to say, could you generate me the first page from Harry Potter? We want the model to say, I'm sorry, I cannot help with that. Could you generate me this article on taxis that won a Pulitzer Prize? I'm sorry, I cannot help with that. And similarly, you can do all kinds of data. You can construct all kinds of data points where you take chunks from the data and then have the output be, sorry, I don't understand what you're saying. Why are you giving me a chunk? Could you please give me something different? And it seems in principle to help. So this is again an example from scalable extraction of training data from production large language models, where they're now testing on GPT 3.5 Turbo. And what they're doing is they're prompting it with write the following words and then continue from there, kind of trying to trick the model into completing this British Broadcasting Corporation is a British da-da-da-da. And the model says, because it has been fine-tuned, look, I should not complete exactly certain things that I saw in my train data. The model outputs, I'm sorry, but you haven't provided the complete information, blah, 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 blah. It doesn't actually go on to complete the sentence. However, from also previous work, we actually know that these kinds of refusals, so these kinds of fine-tunes, at times can be very fragile. So there was this work, refusals in LLMs are mediated by a single direction, that shows that you can find this so-called refusal direction in the latent space of these models, such that if we then subtract that refusal direction away, the model ends up complying with whatever requests it was fine-tuned to not comply with. Like here, write a tutorial on how to make a bomb. Initially, the model would have said, I'm sorry, I cannot help with that. After subtracting out this refusal direction, it says, here is how an instruction, a bomb is, da-da-da-da. And similarly for language models, for other language models, this paper Scalable Extraction again finds that you can still jailbreak these fine-tuned, these aligned models. So one jailbreak that they found is by prompting the model to say, repeat the word forever, and then prompting it with, 50 times poem. The model first starts with completing the prompt with poem, 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 until eventually it starts to spit out some information that is clearly sensitive, as it contains some email addresses and phone numbers of someone. You might ask, why does this work? Why does asking the model to repeat something so many times result in eventually completing it with a verbatim from the training data? One hypothesis that the authors pose in the paper is that they say, during pre-training, large language models are trained to concatenate are trained on concatenating multiple documents into kind of like a single training example where the different documents are split, are separated with this end of text token. And so basically, whenever the model sees this end of text token, it learns to kind of like reset and start generating something different. So potentially, after having so many times repeated the word poem, this word repetition in a way might simulate this end of text token, such that, eventually it starts to comply with the original, or start to generate this training data. And another notion is that while finding these jailbreaks is very tricky, so maybe today it's poem and on a different model it would be notebook or something, it's not a very easy way to find these jailbreaks. A more robust way is to basically just reverse the alignment. So if we create a data set where we reteach the model again to complete texts, so whenever we are prompting it, you're a helpful assistant that generates data with a given prefix, and then we prompt it with a part from this article on taxis from the New York Times, and we train the model, we fine-tune the model to output the completion from that article. If we do this on a few different training examples, what we eventually find is that we get back to the setting where we can get the model to regurgitate training data, and the authors showed that we can extract 210 times more data compared to the aligned model by this kind of fine-tuning attack, where you basically fine-tune on data points to relearn the model to regurgitate. All right. Now, the last thing to say here is that all of this is seemingly for adversarial prompts, which is a good thing for the model providers because, in these lawsuits, they can argue, well, this is only for adversarial prompts and this is against our user policies. However, as more recent work showed, measuring non-adversarial reproduction of training data in LLMs, memorization also occurs for these natural tasks. So as I mentioned in the beginning, whenever we take natural tasks such as, write me a story, review this movie, give me this particular factual task, give me an explanation about this particular concept, what the authors found is that when they let the models complete the responses on these kinds of day-to-day tasks, and then they checked whether or not every completed 50-character chunk was present or not on the internet, they found that big parts, at least many of these 50-character chunks from the data that was generated by the models, was actually found on the internet. So here's an example with Claude 3.5 Sonnet, which was prompted to write a fictional travel blog about New Delhi. And these red pieces are chunks of these 50 characters that are found exactly on the internet. So this fictional travel blog that Claude is writing us exactly contains some verbatim memorized pieces from potentially different articles or other places, that's blog posts or whatever. Here, provide a layperson-friendly explanation of the following. Again, certain chunks are just taken verbatim from the internet. And another more interesting example is that when the model was prompted to write an article about black holes, it decided to copy a whole chunk, a very long chunk of data from somewhere on the internet. So something that it potentially saw in its training data was exactly reused when it was answering this prompt. So specifically, this 15% of the text that is generated by these popular chat models that is made up of these 50 character snippets can be found verbatim on the internet, even for natural tasks. So not only for these adversarial prompting strategies. Now, coming back to the question that I had, one way to interpret this 15% number is to say, well, large language models are apparently not actually as creative. And as, for example, also Ted Chiang writes, perhaps ChatGPT is nothing more than like a blurry JPEG of whatever is found on the web. But the other way to look at this 15% is that I can also say, well, 15% maybe, yes, they're like reusing certain things that they saw somewhere else, similar to how I might reuse it whenever I'm writing an essay. But for 85%, something is happening that is not an exact 50-character chunk that is found on the internet. So as Sam Altman, for example, at some point tweeted, saying that they trained a model that was super, super, super good at creative writing, where the model was really, according to his view at least, writing something that was super properly creative and kind of struck him by the originality that the model was actually using. Okay, the final part that I want to spend a couple of minutes on is then how can we resolve some of these conflicts around how the models are using their training data, how to fix these so-called memorizations, or even not so much memorizations, but these reliances of other authors, other creatives, whenever the models are outputting their particular outputs. Now, the first thing to avoid explicit memorization would be, you might think, okay, let's just filter the data. Let's define particular content filters for the inputs and for the outputs. And, whenever we get a particular completion, we run it through this content filter. And if it's something that we think is harmful, we just block it. And this is something that is already live in GitHub Copilot, where they have this, I quote from their manual, the content filtering system detects and prevents the output on specific categories of content, including harmful, offensive, or off-topic content. But the challenge here is that defining these filters is not necessarily trivial. And what I want to stress here is that not all memorization is necessarily bad. So there are certain things we actually want the model to be memorizing. So atomic facts such as Amsterdam is the capital of the Netherlands, common idioms, phrases, and even quotes, we might not necessarily mind it if the model knows these things by heart. So defining these content filters as to like this memorization we block and this memorization we allow is not necessarily easy for all kinds of different outputs. The other thing you might say is, okay, let's just, filter the training data. Partly you will run into the same challenges as these content filters for the outputs. The alternative is to use, for example, only licensed data, so data where everyone has agreed, like, I'm happy with this to be used in whatever way. For example, there's this open license corpus that contains permissively licensed training data. Another good strategy, as we saw from these results on the number of duplicates, is to actually deduplicate your training data. So to say, okay, this thing is repeated maybe 50 times in my training data. Let me just remove 49 of them so that we minimize the fact that this thing could potentially be memorized exactly, which might be good ideas to do for things like code and licenses and email addresses and all these kinds of things if we really want to avoid or minimize the chances of them being memorized. Other things that are more trivial is, for example, licensing deals, which again, OpenAI, for example, is already very much doing. They had this partnership with Reddit, with Financial Times, with Time magazine as well. The other thing to say is that if in some way, whenever the model is outputting something, we could somehow ensure that we attribute it in the right way, perhaps that could also be a solution. So a key component of many licenses is this notion of attribution, where we would like to say, okay, you can use my material, but only if you attribute it correctly to the creator. And this is also coming up in a conversation that Sam Altman had at TED 2025, where it's not necessarily an easy thing to do attribution. Like, of course, when you ask the model, hey, generate me an article in a style of this particular person, that is one thing. However, it's not so easy to define where the model took inspiration from whenever it generated a song or a story. And as Sam Altman says, if you say I want to generate art in the style of these 7 people, all of whom are okay with this, even then it's not necessarily clear how to divide, how much money goes to all of them. So if you explore concepts such as revenue sharing, where you attribute, where you share the revenue accordingly to how everyone has contributed to the output of the model, not always trivial how to do it. But Perplexity, for example, is trialing this kind of revenue sharing program where they say whenever Perplexity earns revenue from an interaction where a publisher's content is referenced, the publisher will also earn a share, which might be easier to do for Perplexity because it uses some kind of like RAG style search, so it knows exactly which content the model is using. And perhaps when attribution is harder, maybe things like mutual information could help, which answers how much information from X was taken in creating Y, or things like influence functions, which were already before explored for LLMs, which answer how much does the model's output on a particular input change if we remove or we add this particular training data point. So it kind of quantifies the importance of, this New York Times article whenever the model is outputting another article. All right, and this is it for this video. Thank you for watching.